it is 4 o'clock, and I want to give Brendan the full hour so that he can present. So, Brandon, thank you so much for hosting today.
Well, thank you very much, Rebecca. It's my pleasure to be back at Stormwater Awareness Week. I was thinking that I've been around this for, I don't know, about 8 or 9 years or something like that. Maybe this might be uh, the fifth time I've actually presented. So thank you again for all that you guys do to put this on. Well, hello, everyone. My name is Brendan Coyne, and I represent a company called Clear Creek Systems. I provide water treatment systems here in California, and I hope everyone's ready to learn a little bit about industrial stormwater treatment. While everyone is still showing up and kind of logging in, I see the admit button keeps coming up. I thought I would talk just a little bit about Clear Creek Systems, just the background while everybody's coming in still. Clear Creek Systems started business in Bakersfield, California. We're a California company, started in 1994. We started treating water produced over there, down there in the oil fields there. And then we grew into a company that specialized in customized treatment solutions. And now we have offices all over the country with our newest branch in Florida, soon to be opening a branch I believe it is in Maryland somewhere. Yeah. So here at Clear Creek Systems, we are here to provide a wide range of equipment and technologies. We're pretty much technology agnostic in terms of solutions that we sell, though. We don't sell a widget, we sell a solution. And the solutions we provide are meant to be efficient, cost effective, and safe, and easy to operate and maintain. So what we've learned in 30 years of business is that all industrial stormwater treatment sites are unique. There's no exact formula for success. It is often a combination of technologies that comprise the final solution and ensure compliance. And when I talk about compliance, I'm talking about complying with the industrial general permit, both as it is written now and how it might be written into the future. So we're not in a business to supply you something today that will not be able to work in the future with increasing regulation. So today I'm going to present to you some of the key techniques and potential configurations that are used to treat stormwater problems. We're going to meet the needs of regulatory authorities, our clients or customers, as the case may be, the workers' needs so they can do their job safely and efficiently. We're going to meet the needs of litigators or other interested third parties. And finally, I guess what it's all about is meeting the needs of the environment. Make sense? So planning ahead saves a lot of headaches, and that's something I want to drive home here today is, by planning ahead, we'll reduce unplanned expenditures, overspending, and using solutions or technologies that are less than ideal. A systematic approach is directly related to cost savings here. And with that in mind, I'd like to start kind of like at the top, at the very beginning. So this is what planning kind of looks like, if you ask me. We need to take a look at, in a holistic view of the facility and the current situation. We look at the stormwater pollution prevention plan. We look at NOIs that are on the SMARTS website, give a great history of what our clients have been up against. We'll take a look at any drawings that are available of the existing facility so we can get a good idea of the layouts. We're going to know which permits are going to apply, and we're not going to forget about any local city, state, county permits that will need to be procured if we're going to put in a treatment system. by the way, those are the long lead items if you're doing any site work there. We also want to know everything we can about where that water, where our water is going to be drained to, whether it's a storm drain, estuary, the bay. We need to take that into consideration. And lastly, and most importantly, in a way, are contaminants of concern. We'll look at, again, the analytical data provided by our customer client. We'll also go into SMART's database and see if we can get a historical perspective. And we're going to look at what these areas are. And I have here listed pH, turbidity, TPH, metals, bacteria. There could be any number of contaminants of concern. When we supply our services, we want everyone to have made all other attempts to get in compliance. That means all your BMPs are being complied with, all your housekeeping attempts have been completed. In a way, your treatment system needs to be a last resort for compliance. These things, they cost money and they take time and they have ongoing costs. If you can in any way take care of your existing facility without a treatment system, you should do that. This should be a last resort. Nobody wants to spend money that they don't have to spend. And usually the customers that need treatment are, they have tried everything, but I just want to underscore that point. So when a project does come to us, the problems are often due to one of these problem areas. And I'm not sure if everybody would not have heard these terms before, but I'm going to mention them. TSS, also it's called total suspended solids. It's short for total suspended solids. Oils and greases get in the stormwater from leaking trucks or any number of machines that might be operating. pH could be out of whack. Total dissolved solids. So these are solids that, won't get caught up in a coffee filter or a paint filter. They'll just move right through, like water. Metals, including dissolved metals, VOCs, BODs, COD, bacteria. These are some of the main constituents that we see consistently through a lot of our sites. Once we know what we're up against, we can start to determine treatment. And this is kind of my most important slide that I want to show. And if you take nothing else away from this presentation, I'd like you to be familiar with this slide. So for each problem encountered, there's a best practice and sometimes a combination of best practices for treatment. There's no formula. There's no off-the-shelf product that is going to work every time. Each site should be looked at on its own. And that's what we try to do. Technology providers should come up with a system for treatment that is effective and cost efficient. You don't want anybody trying to sell you a reverse osmosis system if that's not what you need. Okay, so effective and cost efficient are a baseline that we need to stay on. Any provider of any of these stormwater treatment technologies should offer bench testing with actual stormwater from your site that incorporates the proposed treatment technology. We will do this to kind of ensure effectiveness. There's also something called pilot testing, in which a system is put at the site temporarily to prove treatment. It's effectively tells you how well it's going to work before any large capital outlay. So bench testing always, pilot testing sometimes that's the best option. So what bench testing is composed of is during a stormwater event, you collect a volume of water, 35, 50 gallons, and ship it on ice to a treatability lab where the treatment provider will replicate a treatment system that they are proposing for your site. And we take your influent water quality, compare that with your effluent water quality after a bench test, produce a report for you to show how effective it was. From there, a final determination can be made on a permanent treatment system. It's effectively an insurance policy on your treatment. It's very important, and I wanted to take a minute to kind of emphasize that. So the problem areas often start with things like TSS and pH. TSS, total suspended solids. It can be comprised of a lot of different materials, clays, organic debris, I should say, metals that get flaked off, uh, even even things like leaves and so forth like that. pH is it can play havoc with your water chemistry if it's not in the neutral zone. And whenever we're treating uh, stormwater, we want to make sure that these two parameters are under control. It's usually the first place we'll start. I'll often talk about TSS and turbidity, and while they're different measurements, they are related, and they often go hand in hand. Turbidity is used as a surrogate measure for TSS because it allows for rapid automated analysis of samples. You can measure turbidity in the field, on the fly, online, right away as existing water quality. You don't have to take a turbidity measurement at an analytical laboratory. It's more convenient for the frequent or continuous monitoring. However, for the lay people, it's crucial to understand that turbidity and TSS are not measuring the exact thing. Turbidity measures the clarity or the cloudiness of your water based on light scattering properties. TSS is a direct measurement of mass particles suspended in the water. Hope that makes sense. So I like to use this slide as an example of how TSS and turbidity are related. On the jars on the in the picture, the one jar on the left has high turbidity and high TSS. The jar on the right has lower turbidity and lower TSS. You see that the solids have settled into the water, but not all of them. You see it's still kind of a haze in there. And just to give everybody an idea how that changes over time, you could set that jar there on the left and it will turn into the jar on the right over time. But it all depends on what's floating around in there. If you have gravel, if you took one of these jars and filled it with gravel and water and shook it up, the gravel would fall out in what, a second or so. Coarse sand might be 48 seconds. Fine sand, now we're over 2 minutes for fine sand to settle out, like you see in the jar on the right. Silts, clays, colloidal particles all have long times to settle out if you just set them there. I don't know if you ever saw puddles on the side of the road, and they look like chocolate milk, and they stay that way for days until the water evaporates. Those are signs of clay in your stormwater. And one other thing before I move on, I want to note that the settleable solids on the right jar. I'm going to kind of refer to that in a little bit later, but it's in a couple slides. So with reference to water chemistry, I know probably everybody knows the pH basically is, but it's important to understand that it is a logarithmic scale. We want to be as close to neutral as we can. Often we want to be as close to neutral as we can before we discharge. High pH is more alkaline, low pH is more acidic. And the other thing that I just want to remind people of is that pH is a logarithmic scale. So a pH of 5 is 10 times more acidic than the pH of 6. And a pH of 5 is 100 times more acidic than a pH of 7. All right. So once BPs are in order, and there's not really a lot you can do to affect pH at your site if it's not in the neutral range. And when we discharge stormwater, we shoot for between 6.5 to 8.5 on the pH scale. I think the rule is 6 to 9 by the permit, but each site is different, and pH issues can be the result of a lot of different things. Some industrial processes and materials, atmospheric deposition or run-on from other sites, exposed materials, typical iron, uh, other chemicals, or raw materials, I should say. Materials of construction, some of those galvanized roofs like to give off zinc, for example, exposed concrete surfaces, leaching alkaline compounds, um, other natural factors, uh, including the local geology, can influence the pH. And also decomposing organic matter can affect pH as well, like algae in your ponds, for example. Things to keep an eye on. So, of note, pH no, pH can be used as a tool to reduce contaminants in your stormwater. So pH changing up and down can be beneficial to treatment. It will all depend on your particular situation at your facility. All right, if you remember those two jars in the earlier slide, the one jar that had the solids separate into a layer on the bottom, we kind of use a grown-up version of those two jars in these photos, except we call them ponds or sumps or tanks. And here we collect stormwater into a central area, allow stormwater to settle out as much as it can, thereby reducing TSS. It also allows for an overall pH baseline for the entire facility. So if you have a particularly acidic area of your property or basic area of your property draining, the rest of the water may tend to dilute that into a neutral solution. So this serves as the main collection area. And if we can use the main collection area rather than a lot of different satellite collection areas, we're going to end up reducing a lot of the costs for treatment. Okay. So on this slide here, I represent that collection basin, sump, pond as the brown box here at the 9 p.m. position called basin, sump, pond. And this is where, in my little scenario here, all the stormwater will accumulate. It allows for the settleable solids to fall out. And from here, we're going to kind of take a deep dive into a treatment train and explain the basics here in an industrial stormwater treatment system. Not all of these components will be required. Some sites might require more different components. This is just an introduction into what a treatment train would look like for industrial stormwater that had a lot of different problems. For a high acre site, these systems can become quite large. We want to plan drainage to the collection point or our basin, sump or pond. We want to try to use gravity to move water around, or do we have to pump stormwater from one site to the other because gravity doesn't work in our favor? Things to talk about. These are things that we should plan for. Is there space for treatment near the discharge point? Or are we going to have to pump a long way to discharge treated water? Is there electrical power at the site? Is that a concern where we need to bring in power poles? One thing that is important to note that, sometimes people don't have a lot of space on their sites, and we need to be able to work around what they do have available. if there's no space for a treatment system, what else can be done? Sometimes uh, there's no space or space is at a premium. We can put a tank underground. All right, so this would be an underground water storage tank in this at this facility. Um, there are a lot of different options, but um, I do want to point out that this time of year I'll always seem to get a Stormwater Awareness Week notification. It's perfectly placed because it kind of helps me transition into like the stormwater season, and I'm reminded that the dry weather installation is always preferred when compared to a wet weather installation. Uh, if you have a problem, now is the time to start the planning. Don't wait till your next uh, lab result comes back and shows you still have a problem. There's nothing wrong with doing a little planning right now, so you can be ready. Once the storm season approaches and we start to get inundated, um, that's the busy season for companies that do what ours do. All right, so first in line is often the first one that gets helped, and the timeline gets extended when everyone waits to the last minute. Um, that could uh, that could potentially lead to increased costs, increased fines, a need for overtime. Uh, Basically, I don't want anybody to have to spend any money that they wouldn't have had to spend. So I'd want to know that. So that's why I talk about that. So we're in our storm season now, and we have our collection basin, pond, or sump. Some solids will stay in the basin, just like in that jar I showed earlier. Um, but we're going to start to need to treat water so we can make room for the next storm coming in. And you guys, um, hope you're ready to go through the process. This is kind of a bit of a deep dive, but this is exciting stuff here, and this is where the magic starts to happen. Okay, this is the crux of what I wanted to present to you guys today. So from our sump or basin, we need to start pumping that water. The water that comes through for treatment is often pumped with one of two styles of pumps: submersibles, which can be completely submerged into a pond, or trash pumps, which sit on the side of the pond or pump. And they each have their benefits, but submersibles can be submerged or float on the raft. The trash pumps usually sit on the side and can be electrically powered or powered with an engine, a diesel engine that accompanies that, or a generator. Either one could be powered with a generator. All right. So these are the common ones that are used for pumping out of our pond. What's that pond look like? It could look like a lot of different things. And I'm not saying this is an industrial stormwater treatment pond, but they can get really murky and dirty. Um, and in this case, we have our pump set, and uh, we have our submersibles, which are floating on a raft. If we put a submersible pump into the bottom of our treatment pond, sitting on the ground, we're going to be stirring up a lot of that stuff we want to settle out. So rather than sucking up all that muck on the bottom, we usually try to suspend them either floating on a raft or some other means, so we're not sucking right from the bottom. Same if we're going to use one of those trash pumps that aren't. We'll put the intake for the pump slightly above um, the ground level so that we're not sucking in all that dirt and the debris. Um, so this one safety thing I like to point out too, every time I show this slide, these ponds can be muddy, they can be slippery, and the sides can be steep. Please consider putting like some kind of flotation device there in case somebody falls in and they can't get out. Say like they're doing an inspection in the middle of the night. for Thanksgiving when nobody else is around. There needs to be some thought given to that if you have a unsteady area to work around these ponds. All right, so we're pumping from our basin sump pond into some settling tanks. The idea of these settling tanks is to give another area for water to settle out. So we have our basin sump pond. It's dirty. You saw the picture of what that could look like. Now we're pumping water out. We're going to be able to get water into these tanks and settle out some of the solids that get swept in. And these tanks also allow for a little bit of equalization from the water that's pumped in from the sump and pond. So you can imagine in a rainstorm, you may get inundated into your basin, sump, or pond. These settling tanks allow for equalization, which means a steady flow rate through the rest of the system. It's kind of a buffer. So a lot of things going on with these, but we're getting additional settling and we're equalizing flow so that we can operate at a steady rate of flow. Of note, one could use another pond instead of these tanks. I didn't show that pond because I thought I would just mention it, but you don't have to have tanks if you have the real estate for another pond for settling. Okay. Some quick notes on tanks. Commonly known as frac tanks, or used to be known as Baker tanks. They're pretty easy to come upon. They're not that expensive, especially if you if you can find one used on the market. They're a little tight at the moment, but they come and go in terms of how available they are. Good rules of thumb: these tanks are obviously transportable. They're don't require any installation on site. They'll store from anywhere from 18 to 2,100 gallons of capacity. The number of tanks or the total gallons of storage is based on a flow rate. We like to have for every 100 to 200 gallons per minute, we'd like to have about 20,000 gallons of storage space to allow things to settle out. And why we ask for that is if there's a lot of turbulence in that tank with, let's say, like we had 1,000 gallons per minute going into one of these tanks, it's going to create a lot of turbulence in there, and nothing's going to settle out because it's going to constantly be, a toilet bowl in there with the amount of water. So we like to keep it anywhere from 100 to 200 gallons per minute per 20,000 gallons. We can push that up to 200 or even more with good quality water with not a lot of settleable solids in it. But high solids content water needs more tankage. All right. Again, the idea is to slow the velocity of the water down so solids can drop out. A couple of handy facts, just to kind of give a perspective. An inch of rain over 1 acre site, you're gonna collect about 27,000 gallons of stormwater. And again, the frac tanks at 18 to 21,000 gallons. So you probably would want to get at least one or two tanks in that scenario. But if you have multiple acres, you can do the math and figure out basically how many tanks you might want to have. All right. So now we're going to move on to another transfer pump. It's very similar to what I already showed you. Nothing too different about this, except that we hardly ever see submersible pumps in this area. It's always going to be a land-based pump that's hooked up to some kind of electrical power there, and these pumps are sized for your treatment rate. So if your QUISP tells you need 400 gallons per minute, you're going to get a 400 gallon per minute pump, and that pump is going to be sized to overcome the pressure drop through the various treatments that will follow. Okay. Now we're ready for some filtration, and professionally, I like the use of a sand filter, and I'm going to talk about that sand filter a little bit. There are different types of filters, bag and cartridge filters. The thing that separates the sand filter from the bag and cartridge filters is that when the bag filter fills up, somebody has to stop the system or close off flow to the bag filter and open it up and change out the filter sock that goes in there, and then put put it back online. And I've been around long enough to know that that's very inconvenient when everybody's off at Christmas time and New Year's and Thanksgiving. Or if they have other work to do at the plant, they cannot be running out to the water treatment system to change bag filters every 5 minutes, 10 minutes, hour, 12 hours, what every day even can become a nuisance. I like the idea of the sand filter because sand filters will automatically backflush themselves. They'll automatically clean themselves. Each one of these three pods I show here um, contain a layer of sand and gravel, and water flows through the top to the bottom and out the bottom, in this case to the left. Okay. And on prescribed intervals or on a pressure differential, the sand filters with these of the control panel there will backflush themselves. And where does that water go? So you're going to have a layer of silt and grime or whatever uh, start to layer up on top of the sand. So we backflush that sand filter automatically all the way back to the settling tanks. It could also go into the basin or pond. Um, the by backflushing on a regular basis, we're able to keep water flowing at the prescribed rate without anybody being responsible for changing out bag filters. All right. So it's the sand filter by itself will remove particles down to about 50 microns. So suspended solids down to about 50 microns. But you might be asking yourself, well, what if the particles are less than 50 microns? What if my water looks like chocolate milk and I can't see any solids in there? Well, another reason I like to use the sand filter is so that we can introduce something called a polymer. And I recognize the term polymer might be new to some people here, so I'll just take a minute to talk about polymer. Um, Polymer is basically a substance that is manufactured to bind smaller particles together. So if you have a bunch of particles suspended in solution, like I show on the jar on the left there, the particles will are usually charged particles, and often they're negatively charged particles. And those negative, just like a magnet, if you put two south sides of the magnet together, they repel each other. That's kind of what's going on in here, except it's going on with particles instead of magnets. So they're all repelling each other, not allowing gravity to take its toll, and these particles are staying in suspension. If I introduce a polymer to this water, the polymers, let's consider the polymer a positively charged liquid that binds up with the negatively charged particles in there to create bigger, bigger particles. And by creating bigger particles, now we're able to send that water through the sand filter, and now they'll get caught up in the sand filter. Often, with the correct polymer selection, we can reduce turbidity to 10 NTU after sending the water back through a filter. And that's kind of what's represented in that picture. So one is prior to polymer introduction. The jar on the right is with polymer introduction. Okay. So how do we know if polymers needed? Well, we're going to have when we do our initial site reconnaissance, we're going to know if TSS is high. We're going to know when we do our bench test that PSS is high, and how certain polymers will react. And we're going to measure that coming into the system. And if you follow the red arrows up to the top left, usually polymers injected right there, and those particles are given a chance to bind up and fall out into the settling tanks. If we inject polymer there into the settling tanks and we go around to the sand filter and we're still having an issue with turbidity, which is related to TSS, we can go into something called a recirculation mode. And that we're just going to go in a circle, follow the red arrows if we're out of compliance there. If we're out of compliance, we're going to, again, retreat with additional polymers. And if there's a reason why our turbidity remains high, those tanks will fill up. Obviously, the water won't be allowed to go anywhere. It'll go in a circle. And once they reach a high level on that tank, the system will shut off an alarm, and somebody's going to get a phone call that there's a problem. What is that problem often? Sometimes you lost your polymer. You're all out. It stopped injecting it. Or a hose came loose or something like that. But the whole idea of this active treatment system module is to continuously to treat for, monitor turbidity and pH. It controls and injects the polymer that is used to reduce turbidity, and it helps comply with permit regulations. It also features the continuous ability to monitor your system. It can connect to telemetry where you can dial in and make sure everything's going right. You can download data to your laptop. You can do basic adjustments to your polymer injection system or your pH correction system, and that means save a lot of heartache, not really knowing what's going on. When you're at home eating your Thanksgiving dinner, you can go right on and make sure everything's looking in good shape there. All right. So as we saw in my previous slide there, the fine particles can get through our sand filter. If we dose the stormwater with a special polymer, our first go-to is something called chitosan. It's called chitosan, chitosan, and that is made from crustacean shells. It's a natural polymer that is often used in the stormwater industry, and that causes these particles to form a flock. And as we look at these photos, you can kind of see what no treatment looks like. And we add some polymer, do a jar test, if you're familiar with that. You can start to see these particles like clumping up together in little chunks, right? They're becoming bigger and bigger. And as they get heavier or less buoyant, and the charge on the particles starts to equalize, they start to fall out. And a lot of times it doesn't take a lot of time to do that. It's another reason why we ask for about 20,000 gallons of storage for every 100 gallons a minute, is to allow these particles to fall out. The whole idea is to fill up those tanks with sludge and TSS. We don't want, that has to go somewhere. And yes, it becomes a maintenance item. Those tanks over a storm season can, and your pond for that matter, can become feet thick with solids, and you will have to vacuum those out once in a while. But that's the whole idea, is to get rid of this from your stormwater. Again, just some other photos, how that works out. Small particles bind together to make large particles, so they fall out of solution. Particles are then effectively filtered. One other small minor point here, but I feel it's very important, is that if you have a contaminant concern like nickel or copper or lead or iron, and that's coming through in your lab work, and you don't know if if it's dissolved or not, And even if it is dissolved, we find that these metals are often attached to these particles that we're filtering out, so that if we can filter out the particles from the water, we're oftentimes taking out those metals as well. So it becomes like a kind of a double-edged sword there, where we can start to make headway on our stormwater quality. I already mentioned that that we'll, if we know we have a problem with turbidity or TSS, we'll inject polymer at the very beginning of the treatment train, where I show the recirc button or recirc line. But if we're out of compliance with pH or turbidity, we go back for more treatment. If we're acidic, we're going to add some caustic. If we're too caustic, we're going to add some acid. In this manner, we'll be able to keep pH in line and not have an exceedance. And again, the active treatment system module monitors continuously for compliance. So now we have our crystal clear stormwater. As you might have seen on the previous jars on the right, the clear stormwater coming out. Now, from there, we can start to treat at the molecular level with specialty filters. At this point, our TDS and other microscopic pollutants that we can't see is now effectively filtered out. Hope everyone's still with me here. So we're done taking out all the TSS. We have clear water. We have a neutral pH. We can send the water through media vessels that hold various products, and these various products remove various constituents. These vessels, is what we call them, not tanks. We call them vessels. They're sized for the flow rate, and often they're in a lead lag position. The lead lag position is great because with it's the lag vessel will always serve as kind of an insurance policy if you have breakthrough of a constituent on your first vessel. So I'll explain that a different way. Say like we are treating for VOCs in your through the media, they're benzene, toluene, xylene. We have our lead vessel there that will pick up those constituents, but there's a lifespan for the media that picks up those constituents. Eventually, you're going to have what they call breakthrough, where that media cannot handle any more of that constituent of concern, and it breaks through and it appears in your sample of your effluent. Well, if you don't have a lag system, that effluent is going to go right into your stream or water, right? And you're going to have an exceedance. But if you have a lag vessel there, you're not going to have an exceedance, because that lag vessel is now going to do the job that the first vessel did. In the meantime, you can call for a media change out, where the media in the first vessel is sucked out and replaced with fresh media. And that lead vessel will then be placed into lag position. And the previous lag will now be your lead vessel that takes the hit from your site. So hopefully that makes sense. All right. So the media that goes into these vessels is specially selected to treat the remaining contaminants of concern. So there's various medias. There's again used to remove metals, VOCs, or other contaminants, and these are actual medias that are used. Some of the more popular medias, activated carbon. For centuries, activated carbon has been used to treat water and remove contaminants. Often used for treating VOCs, and they can be impregnated carbons that are designed to treat other targeted constituents. We have some zeolites, which can often used to remove trace metals or heavy metals. We use blends of media and still there's other media as well. Uh, really, sometimes they're not enough, and we need to move on to more exotic medias. And I show a picture here of something called ion exchange resin, which is a manufactured product that is designed to remove specific, hard to remove constituents. There's a wide variety of types. There's ones that remove PFAS. There's ones that remove chlorate and other metals. Um, they're pretty pricey though, so we try to stay away from ion exchange resins unless there's nowhere else to go. Again, these are the types of things we'll decide once there's a bench test completed. You don't want to go spending $50,000 on ion exchange resin without doing a bench test to make sure it's going to work. Nobody's going to be happy if it doesn't work and we need to get a different resin. Okay. So we use our experience to select which are best and most cost effective, and the media selected should be part of the bench test that the provider does for you. All right. Getting to the end of the treatment train now. Uh, we we may have a need for other types of treatment, and this is where that would go in. So we've effectively cleaned all the solids, all the water, as much of the TDS as we can get rid of, but we still could have lingering problems. It's at this point, and only at this point, would we consider even higher dollar treatment. And this higher dollar treatment is needs to be protected, and we need to have the highest quality water we could possibly get before we're going into it, because it needs protection. But probably in order of magnitude of cost, we can at this point treat for bacteria and COD by using a UV system. That's basically just UV light. UV light to treat bacteria cannot have any shadows. So by removing all those particles in the water, we reduce the likelihood of shadows and bacteria getting past us. So we always want to make sure that we treat as best we can before we go into a UV system. And similarly with the membrane technologies and RO systems, RO commonly used to remove salt from water. Very expensive, high maintenance, not desired to have them, because if you remove salt water, you're going to get a very brine solution, and that's often hard to get rid of in itself. So we recommend not allowing salt water to come into your facility if that's a problem. Figure out a way to not have that happen. So I know we talked about a lot of these technologies, and there's no formula here. Um, each of these technologies I talk about, I have given an hour presentation on themselves, and I've spared you from that. I tried to keep it at the top level, but undoubtedly there will be some questions. If anybody does have any questions, feel free to contact me, or get more information on your own with the old artificial intelligence that everybody's using lately. Um, so if anybody's interested in learning more, going on a deeper dive on any of that stuff, please let me know. So kind of wrapping up here, with proper planning and implementation, treated stormwater will often be a higher quality than background water levels, which it's really typical that's the case. And then finally, we did all this work. We can now discharge our stormwater without threat of further action. For anybody on this call who is having anxiety whenever they get their stormwater results, analytical results back from the lab, I haven't been in your shoes, but I have seen my customers reach the promised land, and that's available to you. And I wish you luck on any problems you have. If you ever have any questions, please let me know. And with that, I will wrap it up. A quick couple of slides to show you how neat your system should look, and what it could look like. And that's it. Thank you very much. I'm here for any questions you might have. My cell phone is on this slide, email, and I'm happy to give this presentation to any of your colleagues that might want lunch and learn or anything like that. Okay.
Fantastic. Thank you, Brendan. If you have any questions, feel free to put them in the chat. We just got a couple minutes. But it was a great workshop. And if you missed any portion of this, or if you had to leave early or any of that, it was recorded and will be up on our website sometime tomorrow. So you can go back and watch that, as well as any of the other workshops. It doesn't look like we have any major questions, so we might let people out a little bit early. We've got a great lineup of workshops tomorrow, so be sure to head over to stormwaterawareness.org and you can register for any of those. So a big thank you to Brendan, and thank you everyone for attending.